Welcome. In this video I'm going to show you how you can obtain the mode for binned data using Python. I'm using JupyterLab with Python version 3.12. This video will focus on how to obtain the mode of binned data, not so much how to bin the data itself. For that I have separate videos. The example that I'll be using I've already loaded in. I used pandas to load in the general social survey data from 2012, adjusted for some example purposes. I don't need all of its data, I just need one numeric field. So in this case I'm going to be using age. That seemed promising, but I'll remove some missing values. And there's an 89 or older category, so I'm just gonna, it's just an example, so I'm just gonna replace those with 89. Coding is a dictionary in this case, and I use replace with that dictionary to actually replace those 89 or older with the number 89. Just to make sure everything is numeric, I use toNumeric. In a separate video I show how you can use my own library, stickpad that simply has a function to determine the mode for bin data. But if you don't want to use my library, then we first actually convert everything to a list, so we're really with just Python only. I specify the bins with the lower and the upper bounds, and then I'm going to replace all of the scores with the bin actually. So that way we have the categorized data, and then actually they're all just getting their bin number. Then I need to count how often each is in, how many counts are for each bin. So I'll simply loop over all the data and count, set them all to 0 at the moment, and then simply add 1 every time for all of my counts. So in this case, the first category has a count of 138, which is actually the second category because there's also category 0. The frequency density is needed because if the bin sizes aren't the same, then you should definitely use this. Then it's the frequency divided by the bin size, the upper bound minus the lower bound. So I can simply loop over them, over all the keys, and that should give me then the frequency densities. Then the mode is the bin or bins with the highest frequency density. So I'll first find that maximum frequency density and then check which of those bins actually have that. That could be more than one, so that's why I'm using a list for this. In this case there's only one, it's bin number 2 or with index number 2, so that's actually the third bin. Unless this list has like multiple modes, and then perhaps all of them are the mode, so then normally we would say there is no mode. So I'm checking if the length of my number of modes is the same as my number of bins. If so, there is no mode, and otherwise just show me the bin. So in this case 25 to 30 was the mode, or the model bin if you will. Instead of reporting the bin itself or bins itself, we can also report the midpoints. That's simply the upper bound plus the lower bound divided by 2. So we can loop over all our modes and simply get those. There's also something known as a quadratic midpoint. Sorry, the formula seems a little bit off. Now it looks good. That looks like this. It tries to actually have a visual for that. It tries to smooth the data a little bit and then determine where the mode most likely is within this bin. The formula for that looks like this. As you can see, what this needs is the frequency density of not the model bin only, but also of the one before it and the one after it. And then it's fairly straightforward. So that's what all this code is doing, is just looping over and finding the appropriate frequency densities, and then just calculates that formula. So in this case that turns out to be 26.24-ish, a little bit lower than that 27.5 we saw earlier. Alright, I hope this video was helpful and thank you for watching.